Hello students, in the last lecture we have already studied the solubility product. So in this chapter means in ionic equilibria we are going to study relationship between solubility and solubility product. The solubility of a compound is the amount in gram that dissolve per unit volume, means which may be 100 milliliter or 1 liter of its saturated solution. So students, the definition of solubility is a compound solubility of a compound is the amount in gram that dissolve per unit volume. After this definition we have to study the definition of molar solubility. So what is molar solubility? The number of moles of a compound that dissolve to give 1 liter of saturated solution is called its molar solubility. So students, as you have seen that we are studying relationship between solubility and solubility product, and in solubility here there are two definitions. One definition is for solubility and another definition is for molar solubility. The formula of molar solubility is mole per liter, means solubility in gram per liter upon molar mass in gram per mole. This is the formula of molar solubility. Now consider solubility equilibrium, or consider the solubility equilibrium for BXAY. Solubility equilibrium for BXAY. So the reaction is BXAY. This compound is in solid state, which give XBY plus aqueous plus YAX minus aqueous. As we have already known that whenever we dissolve any of the substance, it dissociates and produce ion. So similar here, the solubility equilibrium for AXBY, so BXAY, so BXAY in the solid state, which dissociate and give XBY plus YAX minus in aqueous state. The formula for solubility product is given by the equation as we have already studied. KSP is nothing but a solubility product. So for this reaction the solubility product is given by the equation KSP is equal to concentration of B Y plus raised to X, concentration of A X minus raised to Y. If S, capital S, is the molar solubility of the compound, capital S is the molar solubility of the compound, the equilibrium concentration of the ion in the saturated solution will be, means whenever S is the molar solubility of the compound. Student, we have already studied the definition of solubility and molar solubility. I am repeating here. Solubility of a compound is the amount in gram that dissolve per unit volume, and molar solubility means number of moles of a compound that dissolve to give 1 liter of saturated solution. These two definitions we have already studied, and here we are going to suppose S, capital S, is the molar solubility of the compound. So the equilibrium concentration of the ion in the saturated solution will be concentration of By plus is equal to XS mole per liter, and concentration of AX minus is equal to YS mole per liter. These are the two equation or two values when S, capital S, is the molar solubility of the compound. So this is the equilibrium concentration of the ion in the saturated solution. These two values, we can put these values in KSP, means solubility product formula. So we get, in place of B, concentration of By plus, we have to put here XS raised to X, or in place of AX, concentration of AX minus, we put here YSY. When we solve these two brackets, so we get X raised to X, Y raised to Y, and S, capital S, is common, and the power are under the plus value, means X plus Y. X raised to X, Y raised to Y, S is common, and power is always in a plus value, X plus Y. So this is the simple form of solubility product, and it is the simple relationship between solubility and solubility product, or between solubility and solubility product. I am going to repeating here, or I am going to explain here again. Consider solubility equilibrium for BXAY. So this BXAY in the solid state, when it dissolve in water, it dissociate and produce ion XBY plus aqueous plus YAX minus aqueous. When we write the formula for this reaction, solubility product KSP is equal to concentration of By plus raised to X, AX minus raised to Y. If we suppose that S, capital S, is the molar solubility of the compound, so the equilibrium concentration of the ion in the saturated solution will become concentration of By plus is equal to XS mole per liter, or concentration of AX minus is equal to YS mole per liter. When we put this value in the formula of solubility product, so we get the formula KSP is equal to concentration of X S raised to X, concentration of Y S raised to Y. When we simplify these values, so we will get X raised to S, Y raised to Y, and SX plus Y. So this is the relationship between solubility and solubility product. We can understand this by the simple example. So we will get, here we are taking AgBr, silver bromide solid, which dissociate produce Ag plus aqueous plus Br minus aqueous. Here X is equal to 1 and Y is equal to 1. X is equal to 1 and Y is equal to 1, means the value of X is equal to 1 and the value of Y is equal to 1. So according to our formula, we will get KSP is equal to S into S, means S square. Why? Because X is equal to 1 and Y is equal to 1. That's why. Now for PbI2, so for PbI2, Pb2 plus produce Pb2 plus and 2I minus, means X is equal to 1 and Y is equal to 2. So we will get 1 raised to 1, 2 raised to 2, and S1 plus 2. Student, as you have to understand how we will get these values, means we are having the formula KSP is equal to X raised to X, Y raised to Y, and SX plus Y. So we are putting these values in that formula only. So Ksp is equal to x raised to x, y raised to y, and s x plus y. So we are having x raised to s means 1 raised to 1, y raised to y means 2 raised to 2, and s x plus y means s 1 plus 2. So we are getting 4s cube. The value of solubility product is 4s cube. Similarly here, when we are taking the another example, means aluminum hydroxide, which is in the again solid form, reversible, to produce aluminum 3 plus aqueous plus 3 OH minus aqua. Here x is equal to 1 because the value of aluminum is 1, or the quantity of aluminum is 1, and y raised to 3 because OH minus is 3. So in the formula we will get 1 raised to 1, 3 raised to 3, and s 1 plus 3. When we calculate this value, so we will get 27s4. Ksp is 27s4. So this is the nothing but a relationship between solubility and solubility product. I hope you all understand this. Now next topic is condition of precipitation. In condition of precipitation, one term is here which is known as ionic product, and it is denoted by IP, and another term is, which is you have already aware, solubility product, which is denoted by Ksp. So student, ionic product means IP of an electrolyte is defined in the same way as solubility product Ksp. The only difference is that the ionic product expression contains concentration of ion under any condition, whereas the expression of Ksp contains only equilibrium concentration. So student, what is the difference between IP and Ksp? IP means ionic product. Expression contains concentration of ions under any condition, and Ksp contains only equilibrium concentration. Now there are three conditions. Condition number 1, if IP is equal to Ksp, means when ionic product is equal to solubility product, so the solution is saturated and solubility equilibrium is exist. Second condition is IP is greater than Ksp, so the solution is supersaturated, and hence precipitation of the compound will occur. Third condition is if IP is lower than Ksp, the solution is unsaturated and precipitation will not occur. So these are the three conditions for precipitation. First is IP is equal to Ksp, solution is saturated and solubility equilibrium exists. Second is IP is greater than Ksp, solution is supersaturated, hence precipitation of compound will occur. Third is IP is lower than Ksp, solution is unsaturated and precipitation will not occur. The next topic in this chapter is common ion effect. In this common ion effect, consider to understanding the common ion effect, consider a solution of weak acid, means acetic acid CH3COH, and its soluble ionic salt sodium acetate. As we have already aware that which is the weak, it dissociates very slightly in the aqueous solution. So here acid is weak, means acetic acid is a weak acid, that's why it dissociates very slightly in the solution, and we will get acetate ion plus hydrogen ion, means CH3COO minus and plus H plus ion. Sodium acetate means CH3COONA. It is the salt. It is a strong electrolyte and it dissociates almost completely in the solution. That's why for dissociation of sodium acetate, we will get acetate ion plus sodium ion. Both the acid and salt produce same acetate ion in the solution. Sodium acetate dissociate completely, therefore it provides high concentration of acetate ion. According to Le-Chatelier principle, the addition of acetate from sodium acetate to the solution of acetic acid means this sodium acetate is added to the solution of acetic acid. So the result is equilibrium shifts equilibrium of dissociation of acetic acid to the left side. Thus reverse reaction is favored, in which acetate combined with H plus ion to produce or to form unionized acetic acid. What we have done here, sodium acetate is a strong electrolyte and it dissociates completely. It produces high concentration of acetate ion. When this acetate ion is added to the solution of acetic acid, so it shifted the equilibrium of dissociation of acetic acid to the left and the reverse reaction is favored. When here, if reverse reaction is favored, so acetate ion react with hydrogen ion and produce acetic acid again. Hence dissociation of acetic acid is suppressed due to presence of sodium acetate containing a common acetate ion. So what is the common ion effect? The common ion effect means the ionization of weak electrolyte is suppressed in presence of a strong electrolyte containing a common ion to the weak electrolyte. What is the definition of common ion effect? The ionization of weak electrolyte means here we are taking weak electrolyte acetic acid which ionize acetate ion and H plus ion. So this ionization is suppressed by sodium acetate because it is a strong electrolyte and it dissociates completely and produce acetate ion and sodium ion. So acetate ion is common in both the reaction, means in weak electrolyte and in strong electrolyte. When this acetate ion is added to the or combined with the or added to the acetic acid, the equilibrium shifted to the left and reverse reaction is favored, in which acetate ion again react with H plus ion and produce acetic acid, means dissociation of acetic acid is suppressed. It is known as common ion effect. It is only occur when one is weak electrolyte and another is strong electrolyte and both are containing a common ion. Only the dissociation of weak electrolyte is suppressed. The next topic in this reaction is common ion effect and solubility. For understanding this topic, just consider the solubility equilibrium of silver chloride. Student, presence of a common ion also affect the solubility of a sparingly soluble salt, and you all are aware that silver chloride is nothing but a sparingly soluble salt. So remember, the presence of common ion also affect the solubility of a sparingly soluble salt. We are taking here silver chloride in a solid form which dissociate to produce Ag plus, silver plus and Cl minus, chlorine minus. If we are taking the formula of solubility product for this reaction, so we will get Ksp is equal to concentration of Ag plus and concentration of Cl minus. Now suppose we are adding silver nitrate AgNO3 to the saturated solution of AgCl. Means in this AgCl we are going to adding AgNO3, silver nitrate. AgNO3 is a salt and it is a strong electrolyte and it is dissociate completely in the solution. So the reaction for the AgNO3 is AgNO3 aqueous give Ag plus aqueous and NO3 minus aqueous. So in these two reactions the Ag plus ion is common in both the reaction, but the difference is silver chloride is the weak electrolyte and silver nitrate is a strong electrolyte. So the dissociation of AgCl and AgNO3 produce a common Ag plus ion. The concentration of Ag plus ion in the solution increases owing to complete dissociation of AgNO3. According to Leach-Tetrarial principle, the addition of Ag plus ion from AgNO3 to the solution of AgCl shift the solubility equilibrium of AgCl from right to left, and reverse reaction in which AgCl is precipitated is favored until the solubility equilibrium is re-established. So same procedure is here. If common ion is there for sparingly soluble salt, so the solubility of sparingly soluble salt is also affected, as we have seen by these two reactions. We are adding AgNO3 to the solution of AgCl. So what is the result? The solution of AgCl, solubility equilibrium of AgCl is shifted from right to left. Reverse reaction is occur in which AgCl is precipitated until the equilibrium is re-established. The value of Ksp means solubility product, however, remain the same since it is in equilibrium constant. The solubility of sparingly soluble compound thus decreases. The solubility of sparingly soluble compound is decreases. Means the solubility of AgCl is decreases. Why? Because we are adding AgNO3 in the solution. That's why the solubility of sparingly soluble compound decreases with the presence of common ion in the solution. Means here in this example, in these two reaction, Ag plus is the common ion for in this solution. That's why the solubility of AgCl is decreases. Students, these are the topics in the chapter of ionic equilibrium. Theory part of ionic equilibrium is completed. Only numerical is remaining, which we will study in the next lecture. I hope you all are understand this chapter clearly. Thank you so much.